Okay, so our next speaker is Yukihiro Tagami. Yep. From Kyoto University.
For Japan.
Beautiful town. And he's gonna speak on XC learning via nearest neighbor graph partition and embedding.
Thank you for introduction and the great opportunity to talk. I'm Yukihiro Tagami, research engineer at Yahoo Japan Corporation, and I'm now have been in a doctoral course at Kyoto University. Yes, today I'm talking about extreme multi-level crash running via nearest neighbor graph partitioning and embedding. So first of all, we present the three types of classification tasks: binary classification, multi-class classification, and multi-level classification. On binary and multi-class classification, tasks, we choose single level from the candidates. On multi-level classification, however, we can choose multiple levels. So in this example, both cat and bird are selected. So traditional one versus rest approach for multi-level classification converts the multi-level classification into a set of binary classification tasks. So this transformation makes a set of binary classification tasks. The number of binary classification tasks is the same as that of original levels. So next we introduce extreme multi-level classification. This is a multi-level classification with extremely large number of levels. So in this talk, we talk the problems with 10,000 to 1 million levels. So traditional one versus rest approaches are computationally expensive in both training and prediction. Because the number of binary classification tasks is extremely large. So in one example, extreme multi-level classifier is run to tag a new Wikipedia article by using a subset of the most relevant Wikipedia categories. So in this talk, we introduced two methods based on k-nearest neighbor graph. One is AnnexML, and another is GPT. These two methods employ a k-nearest neighbor classifier inspired by Streak, which is a state-of-the-art embedding-based classifier. Both methods are focused on the prediction, faster prediction while keeping prediction accuracy. Okay, before representing the details, we show one notation. N, M, and L are the number of training example, features, and labels. So training data, feature vectors, label vectors, and classifier are represented like this. So this is the outline of this talk. So we first introduced AnnexML. At the beginning, I'd like to show you a summary of AnnexML. AnnexML is a k-nearest neighbor classifier with graphs in the embedding space. So AnnexML improves the trade-off between prediction time and accuracy, more accurate and faster. This figure plots the prediction time and accuracy for Wiki LSSTC dataset when changing the number of ensemble runners with different random initializations. Horizontal axis represents prediction time in logarithmic scale. Vertical axis represents prediction accuracy in terms of precision at 1. So upper left line indicates better results, faster and more accurate prediction. Proposed running methods improve prediction accuracy. So in addition, approximate nearest neighbor search technique speeded up the prediction time. So as a result, at the same level of accuracy, AnnexML was up to 58 times faster than Streak. Of course, AnnexML achieved better results than recent tree-based methods. So AnnexML makes a prediction by using k-nearest neighbor classifier in the round embedding space, like Streak does. The idea of training procedure is AnnexML is simple. The training points that have similar label vectors are allocated closer in the embedding space. In addition, we speeded up the prediction procedure by using an approximate nearest neighbor search technique. Next, we present overview of AnnexML training. Okay. Each point in the space represents a training sample. First, training samples are connected if two samples have similar label vectors. Then, hyperplanes are run to divide the graph into k subgraphs while keeping the structure as much as possible. In this example, k equal to 3. This partition aims to make both training and prediction faster. So projection matrices are run for each divided subspace in order to allocate connected samples closer in the embedding space. For a given test point, we make a prediction with k-nearest neighbor classifier in the embedding space. Since we constructed embedding space to allocate samples that have similar levels closer, so k-nearest training points to a given test point in the embedding space are expected to have similar labels. So using the round hyperplanes, we determine to which partition a test point belongs to. In this example, test point belongs to partition 2. The test point is projected into embedding space using the matrix B2. Then, k-nearest neighbor in the embedding space are obtained. The empirical level distribution of the k-nearest neighbor is returned as result, prediction result. So we propose 3 improvements of AnnexML to Streak, 2 for prediction accuracy and 1 for prediction time. First, we introduced the running 2 partition data points. While Streak uses unsupervised k-means clustering for this purpose, AnnexML utilizes label similarities between data points. As noted before, AnnexML makes a prediction by using k-nearest neighbor classifier in the embedding space. So for accurate prediction, we should allocate 2 training points that have similar labels into the same partition. So we regard this problem as a k-way minimum graph cut problem and construct k-nearest neighbor graph of label vectors. The computational cost of naively finding k-nearest neighbors for all data points is n squared. However, since label vectors are typically sparse in this problem setting, we utilize embedded index to find k-nearest neighbors efficiently. But in some cases, unfortunately, computational cost remains n squared, even if we employ embedded index. So we ignore some head labels and approximately construct k-nearest neighbor graph. Head labels means the labels that most data points have. So after constructing k-nearest neighbor graph of label vectors, we want to obtain hyperplanes that divide the graph into k subgraphs while keeping the structure as much as possible. In contrast with the common balanced k-cut problem, we need to run a merge class classifier to predict the partition of an unknown test point. In other words, given a test point, we need to determine the partition that a test point belongs to by using the hyperplanes. So we sequentially maximize this objective function for each training point, like a stochastic k-means clustering procedure. CI is a cluster assignment indicator for ith data point by using the current weight vectors. First term is intended to assign approximate nearest neighbors to the same partition Ci. A sigma is a sigmoid function. So second term aims for randomly randomly selected points to not be included partition Ci. In other words, this term makes each partition includes almost the same number of data points. Last term is L1 regularization term to obtain sparse weight vector. Second, we represent how to run embeddings. We first define the relevance score as cosine similarity between embedding vector Zi and Zj. Bc is a projection matrix for partition C. We also present the conditional probability by using above relevance score and the softmax function. Xk is randomly selected from data points in the partition C. Gamma is a scaling parameter. So cosine value ranges -1 to +1. So gamma makes this range larger. To run the projection matrix BC, we minimize the negative log likelihood. The above negative log likelihood is transformed like this and optimized by using SGD with adequate running rate scheduling. Okay, we present approximate nearest neighbor search technique by using graph structure for fast prediction. For prediction of AnnexML, we want to efficiently find nearest training points in the embedding space. First, a test point traverses from ball tree. Then the indexed training points are obtained as a reasonable set of approximate nearest neighbors. The nearest neighbors of the nodes are added to a list of candidates. We start to improve the approximation quality by local search. So the blue nodes represent approximate nearest points at this time. The white nodes are candidates to be evaluated, and the black ones are already evaluated nodes. So evaluate, yes. Yes, like this. After all candidates nodes are evaluated, the approximate nearest neighbor are returned. Using these procedures, since we only need to calculate the distances to a small number of ball centers and subset of training points, we can speed up this search task. Okay. Now we describe the dataset using XLens. We compared AnnexML with some recently proposed methods on the 6 large-scale public datasets. The number of level ranges 13,000 to 600 of thousands. Suffixes of dataset name indicate the number of levels. We evaluated prediction accuracy of methods with precision at k. These metrics are widely used for extreme multi-level classification and ranking tasks. We also evaluated the performances with NDCs at K, but since the results showed the same tendency, we only report P at K. So this table shows experimental results. The bold elements indicate the best performances of methods. AnnexML performed the best in almost all cases. There were especially large improvements for the sets that have larger level space. This table compares the 3 proposed improvements of AnnexML. If we did not use proposed running to partition method, we used the simple k-means clustering method like selectors. We also did brute force cosine calculation instead of approximate nearest neighbor search. Method E, only using method to run embeddings, outperformed Slick on almost all datasets. The proposed partitioning method improves prediction accuracy. Approximate nearest neighbor search method had slightly poorer accuracy. Okay. Next, we present the speed up effect of approximate nearest neighbor search techniques. Okay. These figures plot the prediction time and accuracy. For fair comparison, these experiments are conducted with C++ implementations on single CPU thread of the same machine. Okay, upper left line indicates better results, faster and more accurate. So, AnnexML are represented as blue lines, achieved good results on almost all datasets. AnnexML BF, represented as these green lines, is a variant of AnnexML which does brute force cosine calculation. Comparison between AnnexML and AnnexML BF shows that approximate nearest neighbor search techniques successfully speed up prediction time without noticeable drop in accuracy. Okay, at this GitHub page, C++ implementation of AnnexML is available. Okay, next we briefly represent GPT. GPT is a tree-based method. So GPT divides k-nearest neighbor graph of level vectors recursively and construct binary trees. In other words, GPT replaces nearest neighbor search in the embedding space of AnnexML with tree traversal. Next, we describe the similarity between k-nearest neighbor classifier and the tree-based classifier. Oh, sorry. Prediction with k-nearest neighbor classifier and tree-based classifier are both represented by weighted sum of training samples. So in the case of a simple k-nearest neighbor classifier, alpha is one case. Is xi is the nearest training points of a given test point in certain metric space. So on the other hand, in the simple tree-based classifier, alpha is one case. So if xi is a training point in leaf node which xt reaches. Therefore, we expect that some kind of tree-based classifier can achieve good prediction accuracy as well as that of AnnexML. So we now present overview of GPT training. Again, each point in the space represents a training example. The root node of the tree corresponds to the entire feature space and includes all training points. Training samples are connected if two samples have similar level vectors. Then, hyperplane is run to divide the graph into two subgraphs while keeping the structure as much as possible. So the nodes of the tree is split using the round hyperplanes. The graph feature space graph and feature space is recursively partitioned by hyperplanes. The tree is grown until a node contains a small number of training samples. GPT prediction is almost the same as that of traditional decision tree classifier. For a given test point, we determine to which leaf node the test point belongs to using the round hyperplanes. After a test point reaches a leaf node, the training points corresponding to the leaf node are regarded as nearest neighbor of the test point. So the empirical level distribution of the nearest neighbor is returned as prediction result. Of course, this distribution can be pre-calculated for each leaf node. So objective function for partitioning of GPT is almost the same as that of AnnexML. We sequentially maximize this objective function for each training point, like stochastic k-means clustering procedure. Okay, this table shows experimental results. We compare GPT with recent tree-based classifiers. The bold elements indicate the best performance of method. GPT performs the best except Amazon Cat 13K dataset. Okay. These figures also plot the prediction time and accuracy. GPT represented as blue lines achieved better results. Okay. In this talk, we introduced two methods based on k-nearest neighbor graph, AnnexML and GPT. Okay. Finally, I acknowledge them for insightful discussions and helpful comments for these studies. Okay, thank you very much for your attention.